Welcome everyone to join this webinar. My name is Insugo. I'm a postdoc in Taylor Lickett's lab at the University of Vermont. I have been working on spatial modeling and ecosystem services for a few years. I'm currently joined Project ICP, and also I'm working with Dr. Lonsdorf. The purpose of this webinar is to explain why we need your knowledge, how we can use it, and what are the outcomes from the survey. It will take about 20 minutes, then I can show you how to fill out the survey. Isn't it great if we have a unified index to show relative B in abundance across the United States and its uncertainty? Then we can do more than that. We can analyze national bee abundance, identify place of high uncertainty region, and quantify the effects of land use changes. But let's look at pollination ecology and spatial modeling first. Where does bee live and how we can estimate? Basically, it depends on the site quality. If the site have good nest resources and floral resources, then bee can live there. But bees in surrounding landscape can visit this site too. So we can weight landscape using foraging distance function. There is a general consensus that bee visitation rate exponentially decrease with distance. So we can use this function as our forage function. The remaining problem is how we can estimate the site quality. One perfect approach may be measuring it on fields of different land uses and covers and find some relationship between environmental variables and nest and floral resources. However, especially observing and measuring number of nest sites in field would be difficult and time-consuming work, even though there are lots of publications there. But another way is to use expert opinion. It may not correct, but it gives a general idea. For example, we can assign different habitat quality according to different land use or cover easily. The Lonsdorf model using this knowledge provides quite good result in many landscapes. This is an example of California. X-axis is the index from model, which indicates the relative bee abundance from 0 to 1. And y-axis is bee observation data in the California. The model index fits field observation data quite well. Similar relationship is in Costa Rica, we can find. But in some other landscape, the model index did not fit well. It looks like that some landscape has more uncertainty to predict habitat quality. This current project goal is to incorporate variation and uncertainty of habitat quality. Whenever a person assigns suitability values on floral and nesting resources, a large variance and uncertainty are bothering. For floral resources, there are several factors that we need to think, which are seasonal variation, different resource availability, or bloom duration. For nesting resource, it is more likely depends on management practices. Especially in croplands, there are lots of management actions. Organic farm or conventional farm or mowing, non-mowing practices will make the suitability of floral and nesting resources to have a large variance. However, you can still have some knowledge which land use and cover type will have different management options more than other land cover types. If organic farm in blueberry field is minority, you can have more certainty on the blueberry farm than other farms. Here are the key steps in the research. Step 1 is to generate map of our current understanding of pollinator habitat quality. We are going to elicit estimate and uncertainty of nesting and floral resources in the landscape and generate maps of bee abundance and the maps of uncertainty. Then we understand the consequences of uncertainty and identify knowledge gaps and where is a certain places or place of concern. Step 2 is compare predictions of habitat quality with fine-scale management actions and environmental variables to reduce our uncertainty. We also improve our estimate using parameterization process with a large field data set. But step 2 is not current research goal. We are just focusing on step 1 in this current research. Here is outline. First, we are going to show you how we incorporate knowledge and uncertainty of floral and nesting resources. Then, how we integrate these pieces to show the estimates of quality and maps of uncertainty. Then we can discuss of the survey. Here is the way we will incorporate your knowledge of floral resource suitability. We ask you to assign floral resource suitability on 3 different seasons: spring, summer, and autumn, which are equally determined by 12 weeks period. And you can give your opinion about floral resource availability on a given land use type. Let's think about orchard land cover type. In this survey, the orchard land cover includes this type of croplands. For example, if you think orchard provides medium floral resource availability in spring season, then you will enter the score number 3 in bloom score column duration, bloom score column. Then you can provide your certainty level based on your experience or knowledge that tells you how the value varies with different management practices or landscape context. This is the plot you should look at it before you choose the certainty level. Score number 3 means medium habitat quality, which is interpreted 0.5 value in model, and we provide you 3 certainty level options. Each level option, all certainty level option has same mean value but different variance. If you think the medium quality of floral resource availability of orchard does not vary with management options and landscape context based on your experience or knowledge, then you can choose high certainty level. This means that majority of orchard land cover provides medium quality of resource availability. However, if you think it varies down to low quality to high quality according to possible management practices or landscape context, then you choose low certainty level. This indicates orchard land cover provide averagely medium quality value, but it often vary down to low and up to high. Here you can see. If you think the suitability value can be any value from 0 to 1, then you can select a super low certainty level and leave the bloom column as empty cell. Then finally we can ask you the bloom duration, so you can put one of number between 1 and 12, which is the number of weeks in the selected season. We know selecting just one number may frustrate you, but we are going to use the average value from all other people's opinion. This is the way we can weight the floral resource availability according to the different bloom duration. This slide shows how we can collate different opinions. For example, different person gives different values than uncertainty and uncertainty on floral resource suitability. Here is a real survey example from two persons participated in the first webinar. One person selected score number 2 with medium certainty level, and the other person selected score number 4 with medium certainty level for floral resource suitability on orchard in spring season. Now we can sample the values from those two suitability distributions and repeat the sampled density. Then this red color is now the aggregated or combined distribution for floral resource suitability. Let's say this is our prior or combined prior. This prior looks awkward, but once we get some number of experts, we can get well-fitted prior, and the range of the 90% credible interval is the amount of uncertainty of current our combined knowledge on floral resource suitability from just two experts. This is the example of the differences of floral resource availability among seasons in New Jersey. You can see the difference of floral resource suitability. For nest resources, we are asking nest resource suitability and your certainty level on different nest gills. You should focus on the nest resources provided by a given land use and cover, not just focus on just individual bees. For example, orchard provides high nest suitability for ground nesters. Then you can enter score number 4 and think about the variation again. You can use this plot in this time to choose certainty level. Score number 4 means high resource quality, which is indicating here. So we provide you three different certainty level options. All certainty levels have the same mean value, but the variation is different. If you think it varies a lot with different management actions, then you can choose low certainty level. It can make the amount of variance down to medium quality level to very high quality level, even though the average of the habitat quality level stays still high. If you think it does not vary and the majority of orchards stay in the high quality resource, then you select the high certainty level. If you choose super low, it means any value can be between 0 to 1. So you can leave the score column cell as empty cell. That means once you select one of the number, you should select a certainty level. For unsuitable, you just put the 0 and you don't need to select any certainty level. So and in the same way, we can collate different opinions of nest resource suitability. Here is the real example of those two persons from Eco Region 8. For ground nesters, one selected score number 2 with low certainty level, and the other one selected score number 1 with a medium certainty level on orchard land cover. So we can get the aggregate or combined prior from these two persons. Based on those two persons, our amount of uncertainty is a little bit smaller compared to the uncertainty of our resource suitability, what we had. So still again, our prior will be getting better with the number of experts. This slide shows the differences of nesting resource suitability among gears. You can see different gears has different resource source area. Let me remind of you to what are prior and uncertainty here again. This is current our aggregate prior based on just two people about floral resource suitability for orchard in spring season. If we know direct relationship between field management or environmental physical variable and floral or nesting suitability, then we can get a more accurate prior. More importantly, using parameterization process, we can get a posterior for suitability on individual habitat. However, this is not our current goal, this is our future goal. Our current goal is to evaluate spatial uncertainty of bee abundance using current our combined or aggregated knowledge. Using current survey, we focus on evaluate the amount of uncertainty of bee abundance as well as uh, yeah, bee abundance as well as the amount of uncertainty of bee abundance as well as bee abundance that estimated from the model. The different surrounding landscape influence the bee abundance, and their uncertainty also affects on the uncertainty in certain place. So we like to quantify it. How do we evaluate or quantify uncertainty in a given location? Look at here, there are different priors for different land use cover surrounding place A. We are going to use Monte Carlo simulation. We can assign random quality values on floral and nesting for a land cover. Each random value is selected from their probability distribution. Then we can make different combination for each simulation. For example, we can select for floral resource suitability 0.2, for nesting resource 0.01, and we can put these numbers in pixel 1 of orchard. And we can also put another random value, assign random value on pixel number 2 of orchard. In this way, we can make a lot of combination, random combination. Then we can simulate and we can find. Then we can quantify the bee abundance index that is from the model. Then we can calculate the mean. What is the mean value from those different number of simulation? And then we can also calculate the standard deviation, and we can also point out where is the 5 percentile or 95 percentile, and then we can say this amount of this range is indicating the amount of uncertainty. Then the range of this is now the amount of uncertainty then that can be comparable spatially. Here is the real example for the result of Monte Carlo simulation in a part of 2013 New Jersey. Within 10 kilometers square the area, there are 50 different land use covers: deciduous forests, wood wetland, development area, and the blueberry land cover are dominant land covers in this area. we reclassify this land cover according to the categories in our survey format. Then we ran the Monte Carlo simulation using the aggregate prior from just two expert opinion. Then we can have the mean value for the relative B abundance. So this relative B abundance model index shows here is the relative high B abundance, and this is low B abundance. As you can see, this is open water, so the B abundance is relatively low. And we also provide calculate the amount of uncertainty. So as you can see, this is the region that of high uncertainty area, and this is a low uncertainty area. So even though there are high relative P abundance index we can find here, but our uncertainty is relatively high. And we can project this relationship to a whole state. Then you can see this is a source area, and you also find several hotspots that indicates high uncertainty area. And we are likely to validate our model index using the B observation dataset. Then if we found this relationship, then we can rescale the index of B abundance and uncertainty. So this is just model index, but we are likely to rescale our index to using this relationship. Then our uncertainty index also follows the this relationship. Yeah. Then we can compare the state of B, different states of the B index, model index. So this is New Jersey, this is Connecticut. As you can see, New Jersey, we can find more B's in New Jersey than Connecticut. And we can also make some simple statistic result, and we can also see our P relative P abundance according to state or according to the crop length. And finally, we also using we can use the different crop land data layer. Then we can quantify the land use changes and how the relative B abundance index will change followed by the landscape land use changes. And this is what I prepared for you, and then we can move to on how we can fill in our survey. Thank you for listening, and if you have any question, just let me know.